Thank you. Hope you can hear me well. And good morning, everyone. And my apologies for not being able to be present with you. I really regret missing this opportunity. So this morning, I'm going to give you an update about the status of SCORPIO. SCORPIO is an acronym for spectrograph and camera for observing rapid phenomena. And the real SCORPIO, SCORPIO has 8 legs. The instrument has 8 legs, so it's a very appropriate acronym. I think we were pretty lucky with that. Okay, so this slide shows just a summary of the enormous range of science teams that can be attacked by an instrument like SCORPIO. Of course, SCORPIO has been designed for being a time domain machine. So you can see here the long list of science observations that can be optimally carried out by SCORPIO. And we just heard about kilonova and fascinating stuff like that, but the range really goes from these exotic extragalactic objects or galactic extreme objects, so to speak, to exoplanet transits, for example. On the other hand, when you have 8 channels that can observe in parallel, both in imaging and in spectroscopy as a target with such an efficiency, I'm pretty sure SCORPIO will be highly demanded also as a general facility instrument, because you get simply more data at the same time with a nice gain in speed, in observing speed. The main instrument capabilities are summarized here. SCORPIO, as I said, is an imaging and spectroscopic mode. In imaging, we have 8 channels, and the channels are basically rigid in some way. The band passes are fixed. You cannot put an H-alpha filter, so to speak. You have the broadband GRIZ and the Y, J, H, and K band for the near IR. So you cover for about 4,000 to the K band, 4,000 extern to the K band. And we made an effort to go standard with this band passes, so to get the same type of, almost basically the same type of edges of the LSST band passes, for example. So color corrections when you get the transits with LSST, for example, should be minimal, basically avoided. The field of view in imaging is 3 by 3 arc minutes, so it's pretty large. And it's 180 seconds, and on a 1K by 1K detector or detectors, you get a scale of 0.18 arc second per pixel, which nicely sampled the seeing that has been presented in one of the posters. The spectroscopic channel has, again, 8 channels. The hardware is basically the same, except that instead of filters, now you put VPH gratings and slit on the focal plane, so you get a simultaneous wideband coverage. We push with the spectra a little bit below 4,000, not too much, because we know Gemini has a silver-coated mirror. The resolving power is 4,000 when we use the 3-pixel sampling. The 3-pixel wide slit is about half an arc second. But we have a narrower one, a 2-pixel, and then a suite of other wider slits that will give you a better throughput, of course, at the price of the lower resolving power. Interestingly, the slits are as long as the imaging field, 3 arc minutes. 3 arc minutes is very large. If you're familiar with our cousin, which could be X-shooter at ISO, X-shooter is about a dozen of arc second, if I remember well. So with 3 arc minutes, you will always have a chance. You can basically probe almost 6 arc minutes diameter field. So you always have a chance to have a nice bright comparison star in your slit, which I think is very, very good for monitoring and, to cross-calibrate your source against something, your variable source against something that is not supposed to be variable. Another great advantage is that this instrument is supposed to be, will be reconfigured from imaging to spectroscopy very rapidly. So you can acquire or study your field in imaging and go in spectroscopy. But actually, we try really to push the limit with that and go with the ultra fast target acquisition mode. And this is enabled, as I will show, by having slit viewing camera. So you can put your slit, but you can also see what is around, and therefore you can, if you are off by a little bit, you can just put your source, your target in the slit with a single move, and should be very, very fast. Another nice thing that this instrument has is that the CCDs sort of not conventional. The ones that we use are frame transfer CCDs, and this allows us to drive them very, very rapidly. There is a continuous mode. Of course, the field of view will be smaller, but there is on a small field of view, you can go as fast as 50 milliarc second per frame and do this forever, continuously. Or you can even beat this limit. At some point, you need to take the data out from the CCD, so you need to stop after a while, but you can have bursts of exposures that can be as short as 3 milliseconds. If you have enough photons in 3 milliseconds, that would open a new window in our astrophysical measures. So it's pretty extreme, the range of things that you can do with this machine. Here is a picture. I apologize for the next thing that you're going to see, which is this one, is how Scorpio is going to see. The perspective is completely wrong, but gives you an idea of the size. It's actually a pretty big instrument. It's 2 tons, the limit of what Gemini likes to put at the focal plane, and is divided basically in 2 parts: an optical channel, an optical side, and an infrared side. Here you see better the structure. On top, you can clearly see this half cylinder, which is the cryostat for the infrared channel, and on the bottom, the black side, the black shape, is the visible channel. So they sit one on top of the other, and this has been already shown basically, but this is like zooming in and seeing how this layout is arranged. Let me point your attention to here this green, the green element to the left. This is the first dichroic. The light basically comes from the left through our window in the infrared, but then the visible is immediately splitted by this beam splitter through another window, a secondary window, and goes to the lower floor basically. So it goes in and out from the infrared channel to feed the visible channel. This is another zoom of another view. Basically, I'm opening for you the instrument, showing how these channels are arranged. The infrared is on the top, and at the bottom, almost specular, pretty similar concept, is the visible channel. And the way this works is basically through a cascade of dichroics. The beam is splitted and distributed by basically 3 passages to the dichroic. Here in the infrared side, I will show you the light comes from the entry window and then goes to 1, 2, 3, and 4 longer or shorter and shorter channels, depending on the performance of the dichroic. And besides, apart from this beam splitting, the design is pretty conventional. There is the usual collimator camera with a pupil plane, where in this case we put the VPH gratings. These VPH gratings are mounted on these benches, and they can be pulled in and out. And when they are in, you are in spectroscopy mode, and when they are out, the filter is in place, and therefore you are in imaging mode. The same is true for the other side, for the visible side. I guess you can imagine that the show is the same here. The light is reflected and beam splitted and reflected, etc., to feed the four CCDs. So a key requirement, I think is important to remind there, is that during our integration, that is actually in progress right now, we will make sure that all the 8 focal plane are aligned very, very carefully. And the idea is to have an offset of a couple of pixels maximum between them. So the field should be, the 8 fields should be very, very nicely superimposed. Also important, the 8 fields have basically the same scale, 0.18 arc seconds in all channels. There will be some image distortion. There is some optical effect that changed by tiny bit the plate scale. Is not an issue, of course. Even in quick loop you can correct for that, but the idea is that you will get the same image each time in parallel in all these canonical wideband filters. This is a zoom into the filters and the capability. Wavelengths go left to right here and shows here the 8 channels, GRIZ. The names are here at the bottom, GRIZ, and then we move in the infrared where we have YJHK. There are gaps, they correspond to the atmospheric opacity, H2O opacity gaps, as it is common in the infrared. Y and J are nearly contiguous. The gap again is designed to avoid the regions of very high opacity in the atmosphere, and also to make these band passes consistent with the standard band passes. Also here, the Z band, for example, is short just because it's shorter on LSST. So we really clone what we have. And also in imaging, you see the image start for 400, and in spectroscopy, we push below. Again, we want to have band passes, especially in the visible, that replicate the one that are considered to be standard. This is an illustration of how the instrument works. As I said, 3x3 arc minutes, 0.18 arc seconds is 1K by 1K. The detectors are much larger. There is a lot of, so to speak, wasted space, but that's this comes basically for free. These are the detectors, the science grade detectors, the E2V that we want to use in the visible. In the infrared, we go with 2K by 2K, the Y to RG, and they are 2K by 2K. And again, we need a 3x3. So we will have these fields sitting at the center of our detectors, and they will be limited by a field stop just after the window. We have a selection mechanism that puts the stops. For spectroscopy, it's the same tree in length, but is sitting here in the middle. Is our tiny slit. The spectra in this case are extended over as much as possible and as much as space you have on the detector. So when with spectroscopy, we really like having 4,000 pixels. In this case, we have 2,000 pixels, and we use all of them. And things are arranged in such a way that you get about 4,000 resolution spectra in both in the visible and in the infrared. And then there is this other mode that I was briefly mentioning before. We can put on the focal plane a narrower slit, and with this narrow slit, you can optimize your readout, transferring out the charges at very high rate. And with a couple of clever tweaks, you can push your exposure time to the millisecond range, either in continuous mode or in burst mode, depending on your science case. These basically illustrate the main modes. See here. Okay, this is. I apologize because for these parts at this point we start having really a lot of hardware ready, but this is still a PowerPoint slide, but it's pretty clear. And it shows you how in the focal plane, just after the entry window and before the first dichroic, they push the light down in this hole to the visible channel. Just here in the common focal plane, again, in Shooter has different focal plane. We have a single focal plane that serves all the channels. So very immediate target acquisition, everything is on focus here. We can put the slit, we can put the field stop. This is the point on the right where we have our selection of slits and the narrower mask here at the center. And this is another, and I picked up another feature of the instrument. There are many of them, of course, but this is an interesting one. Here on the right, you see through this hole one of the slits. There are reflecting surfaces adjacent to the slit with a tiny tilt. Is an interesting piece of hardware, this one, and they reflect the off-axis field to a re-imaging system. So when you put the slit, there is here a CCD on the side that will always be able to give you a narrow field around the slit to make sure that you are perfectly centered, the tracking is okay, the seeing stays whatever it is, and especially when you acquire the source, you can see where the source falls after the telescope move, and if you need, do the last final adjustment for fastest target acquisition without having to go in imaging mode and then back and forth, save time. This is, of course, when you have all this, you have to understand, I mean, I think you understand very perfectly, very clearly the situation here. When you go in the blue and maybe there is no moon, you don't want to read the detector. You want to go faint, you want to have long exposures, and then the shorter the wavelength, the faster the changes in the atmospheric transmission, the OH change, the lines, etc. So the integration times need to be coordinated, because certainly what you don't want to do is to move the telescope for a diver move, or to move your target in the slit when one detector is integrating. So there is a lot of attention that has to be paid to syncing the readout modes. And I can anticipate already that the 4 infrared detectors are basically independently driven by 4 readout modules. So you can clock at different speed this stuff. Not that we may want to do that, but there is a significant independency, because even Y and K band may have different requirements in terms of length of exposure. Exposure that in this case for Scorpio, I think unlike the majority of instruments, will be done in non-destructive mode with multiple reads of the sample. We do this on the Hubble and on Webb, which is my background, and they are very effective to understand better what is going on if there is any variation. And they are also great to improve your dynamic range. You hardly saturate sources, because you start with, you get the entire suite of exposure times. When you saturate from a certain point, you still have the early frames in your ramp that you could count. So this is work that keeps us busy, and will keep the telescope operators busy. We don't plan to give you a crazy amount of freedom here, but provide you with optimal combinations, of course, to simplify life, and we're working on them. So the status of the project is, I would say, despite COVID that clearly delayed delivery of parts, the companies, a lot of these parts going cascade, and our lens has to be, you need to procure the glass, you need to polish, you need to coat, comes back. Everything, every lab that stops forces you to a delay. But we made good progress. We are basically at this point, we have delivered almost the
Roberto, we need to finish up.
Yes.
Because it's 1 minute and a half ahead, please, if you can.
Okay, so that's I can certainly close here. I just want to say that the instrument is supposed to deliver in 24.
All right. Questions? First, maybe?
Yes.
Sorry, Ricardo. You're gonna ask.
Oh, me. Okay. Thank you. So I have a question about this high-speed imaging mode. So you show it's possible in this very narrow rectangle. Is it possible to change the RI of that one somehow? That's the first question. The second one, is this high-speed imaging available for all 8 channels or only the optical? Thank you.
It's available for all 8 channels. Of course, the readout, so starting from the second question, the readout is different because you have, it's really driven by how fast you can transfer charges out from a CCD. So this is the key that drives. With infrared detectors, things may be a little bit faster, also because we read the detector with the full 32 channels out, not the 4. So I'm not that concerned about the readout speed in the infrared, but it's really the speed of the CCD and transferring the data out. In principle, can be done on larger areas, but we have only one field stop. The trick is that you have to move the charges that have been exposed to a dark region and start to stop exposure, because you want to take the next one. So this has to be done on windows that are 100 pixels wide. So we move there in the middle. So 50 up, 50 down. The time that it takes to transfer these charges is basically what drives your readout speed. If you want to have 200 by open windows, you don't have that, just because we have this single field stop that down select this opening. And this has been, we thought about, the optimization process, what is the seeing, how large can optimally be. And we ended up with the 18 arc seconds wide region for fast imaging mode is enough to sample bright targets.
There was just one question, Zach.
Hey, great talk. I also have a question on the fast mode. And principally, so you mentioned, it's being able to run in burst mode. And I was wondering how many frames, like in a set amount of time you can take before you need to offload the data. Yeah,
it's sort of easy the math at this point. First order, forgetting the fact that you are also transferring out, but think about the detector is 4K by 4K, and we have 2K on the top and 2K on the bottom. We use the 50 pixels, and then we have 1950 pixels that are in the dark. So they can store the charge and slowly you put them out. But this means that you have 20 slots on the top and 20 on the bottom. Right? Sorry, 50 2000 is 40. Right, you have 40 frames basically you can store on your chip very rapidly. It takes nothing to transfer this 50 pixels in the dark area. Then you start taking them out. The speed is much slower there, and this buys you only a few frames. So I think we'll be about 43, 44 exposures. I don't remember the exact number at this point because it goes with the decimals, but it's less than 50 frames you can take. So 3 milliseconds, if you really go to the maximum speed by 50 frames, you get your number, right? It's a fraction of a second, 150 milliseconds.